All right, so we talked a little bit about me making a little bit of a wrap-up discussion for the Unit 7 activity that we completed in class today. We called it Lab 7R. So let's go through the things that I think would be helpful. First, if you look at the first station where every single group generated a titration curve using the Vernier Lab Quest 2s and the pH probes, you should have noticed that in this case there was evidence that we were dealing with a diprotic acid. And it was a weak acid at that. Just to break it down for you, because we didn't have any connectivity between our iPads and the Vernier Lab Quest 2s. So here's the curve shown in green. And you notice that in this case, I've marked with little red lines the first equivalence point where we've removed that first proton from oxalic acid, and then the second equivalence point, which is actually much steeper. You notice that when you have a diprotic acid, that first equivalence point is pretty easy to miss, especially in comparison to the big steep peak that we see here, the equivalence point, when you've neutralized all the hydrogen ions from the oxalic acid. Now, oxalic acid is a weak acid, so that's why we also see the fundamental, once we've neutralized all of it, that neutralization equivalence point is above pH of 7. So all in all, I was pretty happy with the way you guys did that. You were very inquisitive, and you took all of the equipment and used it appropriately for that. Next, let's move to Station 3. So we're going to skip Station 2 entirely because I think most of the good points came out in the discussion at the end of class. But in Station 3, this was a situation where you hadn't really dealt with a complex ion before, and I think it's helpful to be able to look and see one and think about what's really going on. So recall that we started out with a 1 molar solution of copper 2 chloride. Now in reality, the copper ion complexes with water, forming this hexaamine, or this hexa-aqua copper 2 plus ion. We call it hexa-aqua obviously because there are 6 waters attached to the copper ion, and when you have a metal with ligands attached to it and a charge, that's what meets the criteria of becoming a complex ion. We add a little bit of ammonia, and we notice that ammonia causes some of the copper ions to react to form an insoluble precipitate. The real formula is shown here. In reality, we can simplify things a bit, and I'll go through that in the next slide. Add even more ammonia, and then you just shift the equilibrium position towards a more interestingly colored complex ion, the tetraamine copper 2 ion. So if we break it down to a little bit simpler form, what we have going on is first, when we add a small amount of ammonia, the copper 2 ions are essentially reacting and responding to the hydroxide ions that we're placing in solution and forming this copper 2 hydroxide, which is a pale white-blue precipitate. It's not very soluble at all. Its KSP value for copper 2 hydroxide is 2.2 times 10 to the minus 20th. So as soon as you added even just a few drops of ammonia, you readily noticed the formation of the precipitate. Now, what you also probably noticed was that you also would form, in addition to the precipitate, a little bit of some very deeply cobalt blue solution. But when you mixed it, the majority of it reverted to the precipitate. And here's the things we have to remember. When we first added the ammonia, the system was responding to minimize the hydroxide by the formation of this precipitate, which this precipitate is highly insoluble, so it did a great job of removing it. Removing that hydroxide did not remove the ammonia from the solution, however, and over time, as you add more and more ammonia, you get a buildup of a greater and greater amount until we get to the point where that second process is going to go past its tipping point in terms of its equilibrium position, and you're going to have enough ammonia to cause a significant formation of copper 2, or sorry, the tetraamine copper 2 plus ion. And this shouldn't surprise us as well, as we see quite a dramatic shift because the Kc is so large. It's around 1 times 10 to the 13th power, just telling us that the formation of this tetraamine complex ion is highly favored. So let's go through a little bit with complex ions. Some things you need to know. They are going to contain a metallic cation. Typically it's going to be a transition metal. These are metals that have available d orbitals for forming bonds, and they can form some unique situations because of the availability of those d orbitals. Whenever something's attached to that metallic cation, we call that a ligand. And these are typically species that have a lone electron pair on them that can form a covalent bond with an empty orbital in the metal cation. And if we look at a few of the most common ones, you'll see those lone pairs bright, just staring you in the face. So with ammonia, you see the lone pair at the top, and the cyanide ion also has the ability to form these types of complexes, and water as well, with two lone pairs on it. So we see ammonia, cyanide, and water being able to form some common ligands and therefore some complex ions. So let's look at another example and see if we can make even more sense of it. But before we do that, sorry, I forgot to put this slide in first. The coordination number piece. So you may see a question on occasion where it asks you the coordination number of a complex ion. And that's super simple to identify. You just look at how many ligands are attached to the metal ion. So if there are two, an example here with silver, this diamine silver 1 ion, its coordination number would be 2 because there are 2 ligands attached to it. And I think you get the point from here. You don't need to hear me talk about it anymore. In terms of how we get the K value for the formation of these things, if you think fundamentally, if you look at it, this example here using silver chloride and the diamine silver complex ion doesn't look a whole lot different than what we would do analytically if we looked at the same situation for the copper hydroxide, where copper hydroxide would be our solid substance where we would have a KSP value, and then a sequential kind of process where the metal ion bonds with the ligand, in this case ammonia, to form the complex. And in this case, we just use standard rules related to equilibrium processes. If we want to find the K for the overall process, nothing more than combining these 3 individual processes to give us the overall reaction. Well, the K value is just the product of those 3 unique K values. And K, just like anything else, expresses a ratio of concentrations of product ions over reactant ions raised to their power. And again, notice we don't see silver chloride here, and you might think about why that is. If you had to think for more than 2 seconds, remember that silver chloride's insoluble, and we don't put pure solids in equilibrium expressions. Hope this was helpful. Hope you guys have a good night tonight.